list. My name is Kaeza Fern, and I'm volunteer on for MEER ReflEction. So I'd love to introduce Dr. Tao. Educated as a nanotechnologist and instrumentation expert, Dr. Ye Tao brings the benefits of a multidisciplinary background in engineering and science to problem solving. He has had formal training and research in combinatorial chemical syntheses, custom instrumentation design and fabrication, low temperature experimental physics, mechanistic organic catalysis, semiconductor fabrication technologies, structural biology, and surface science. Dr. Tao recently completed an appointment as a fellow and principal investigator at the Roland Institute at Harvard, where his team achieved the synthesis of a thin metal oxide with record-breaking magnetic properties. In 2020, Dr. Tao founded the MEER ReflEction framework after grasping the accelerating and ultimate consequences of the climate crisis on Earth's delicate web of life. Devoting himself full-time to its growth and research projects, he currently heads the organization. Dr. Tao fosters unrestricted access to science-based education, which he believes is the keystone to changing the current trajectory toward carbon neutrality, ecosystem recovery, and sustainability. So, Dr. Tao, we're so glad to have you. Welcome.
Thank you for the introduction, and thanks to everyone for joining us on this day, wherever you are from the world. So let's get started. So in today's talk, you will see many new slides. Sometimes it's the same information, but we're always trying to find different ways, clearer ways to tell the message and to share the information. So I like to have you, keep a mental note of what you think works, what doesn't work, and in the end, please also be generous and share with us your feedback. Well, let's get started. The work was initiated at the Roland Institute at Harvard a few years back. And the institute was funded by the late Edwin H. Land, who also was behind the construction of the Harvard Science Center. So at the institute, we have about 10 different fellows. So we hire 2 new fellows each year and also several postdocs to join the research of the fellows. And we cover a wide range of engineering and scientific investigations. You will see that I really like to use 2-dimensional plots to make concepts clearer. And you can, for example, plot different areas of science and topics on this 2-dimensional plot where the x-axis is the length scale of the object that you're trying to investigate, and the y-axis could be the complexity of the dynamics of the system you're trying to investigate. So in my lab in 2016, we had the goal of trying to build a scanning microscope from scratch that would enable the imaging of very small pieces of matter, but with very high resolution, atomic resolution, in fact. And if you can find the structure of heterogeneous nanoparticles or protein or viruses, then it's possible to understand their function better and also to design drugs and also therapeutics against diseases. So in order to achieve that very important goal, we have had to take a lot of detour trying to make different types of instruments and tools that goes into this instruments. One example being this very strange looking structure perhaps, but it's a very tiny cantilever beam made of a framework where the whole structure actually is a single crystal of silicon. And this thing is very tiny. So the scale bar here shows 5 micrometers. 1 micrometer is 1/1000th of a millimeter. And the width of these beams are on the order of 1,000 atoms. So this is an object which is almost atomic, but it's a macroscopic object. So I've learned to make these things, carve them out from a single piece of silicon, as you see in the background there. My team also have learned to do subtractive machining with really high depth resolution. So here is an example of the atomic force microscope image that tells the height of the surface, and the color scale here shows from roughly 0 to 6 nanometers. So there's roughly like 5 atoms in each nanometer. So the whole range you see there is on the order of 50 atoms deep. In order to build such tools and make these devices, we have to construct quite complicated instruments to support the fabrication. And this is just one example of the many instruments that were used in the fabrication of such devices. And to make nanoscale, atomic scale machining, we made use of an old electron microscope. We have had to disassemble the whole thing down to individual bolts and parts, clean the whole thing, make modifications, and reassemble everything back, but this time with a lot of add-ons to give it additional functionality. All that is to say that the progress of science and engineering is a very challenging and a very difficult. And the fight against climate change is no exception. Hopefully, like you will see how, like my previous experience in nanoscale science and engineering has been instrumental in inspiring the particular framework that we're currently working on. So we already mentioned that in laboratories generally, we have some targets, some scientific targets or some engineering targets. And we deploy all that's known in science already to inspire engineering of instruments that can lead you to a particular engineering or scientific targets. Oftentimes, the path is not straightforward. You have to engage in side projects to eventually, hopefully, get to your goal. But oftentimes, the new science that you discover in the process and the new tools that you develop can enable attaining other objectives that didn't seem possible initially, and also to make additional tools that are useful for other processes than the original purpose. So all is fun until in 2017, I became aware of the severity of the climate crisis. And with each passing year, the situation is getting worse. So it makes sense to maybe pause for a moment and examine the situation and perhaps leverage our critical thinking and problem-solving skills to ask the question of why, after so many decades of trying, humanity is still on track to a climate catastrophe. So, as a scientist engineer, we should be very critical of any assumptions. And some of the common assumptions in the field include the claim that 100% renewable energies would be sufficient for solving climate change. And there's many different organizations and activists trying to plant trees in their effort, a very noble effort to tackle climate change. And numerous companies and prestigious awards in the tech field are calling for the capturing of CO2 from the air as a method to tackle climate change. So these seems to be correct because everybody's doing them. So perhaps you might also agree that our capitalistic system and the process of democracy as it's currently practiced is also an effective governance method. These are taken as the common sense by most people in our parts of the world. Except if you really became interested in these issues, there are many great thinkers who have pondered these problems. And I would refer you to these excellent thinkers, journalists, and activists on their take on what perhaps could be the fundamental cause of our climate dilemma. But today, we will rather focus on the technical aspects of renewable energy and different proposed solutions for the climate crisis. So here is a very simple model that hopefully would be very useful and recurrent in today's analysis. So we can consider the collection of all greenhouse gases in the atmosphere as a node. And we have a certain rate at which we source gases into the atmosphere or emit gases into the atmosphere. And different natural processes are also taking these gas out of the atmosphere at a certain rate. We can conceptualize the amount of energy, thermal energy trapped in the Earth's biosphere as another node. And it's coming in mostly as shortwave radiation from the sun and going out as long wave infrared radiation. So climate change, as we currently observe, involves the coupling between these two nodes by some mechanism. The specific mechanistic details is functionally equivalent to the collection of greenhouse gases weighing down on the exit pipe of heat, like a spring-loaded valve. So when we ramp up the input of greenhouse gases, we have an increase over time of the size of this node, and thereby a decrease in the rate of exit. And now we have an imbalance of the source and sink rate, which leads to a growth over time of the amount of heat that's trapped in the atmosphere. So the data has been quite telling. Since we started to burn coal in the 1750s, the Earth system, as plotted on this two-dimensional plot, where we have atmospheric CO2 on one axis and the average surface temperature on the other, we have the Earth system going on a trajectory and exploring a region of this 2D space that it didn't really sample over the past million years of its natural history. So it's very important to note that on this particular figure, the different dots are color-coded as a function of how distant in the past the data point comes from. So we see that over the past roughly a century or two, the distance traveled by the Earth system has been comparable to how much would travel, on the order of 100,000 years or 10,000 years in the past. So the Earth system is really speeding currently along a foreign trajectory. You might also notice that the natural region seems to fall more or less on a line like that. And the current trajectory is clearly a deviation from that line. The reason can be understood in this plot, which is essentially the same data, but plotted on a slightly different range. So the Earth system sensitivity or equilibrium climate response is what the Earth system would like to be if given sufficiently long time for everything on Earth to equilibrate, including glaciers, polar ice, and the vegetation patterns. And the reason why we're currently on this trajectory that's different from what the Earth system likes to be on is because of the rapidity with which we are outputting atmospheric CO2. It's so rapid, in fact, that the Earth has time catching up with the perturbation. But the trend in the future, if we allowed more time, is that the Earth would so-called relax or slowly move towards a region that it's comfortable at, which is bad news for us because that corresponds to continued heating of the planet. So these curves that I drew are based on very simple linear models of past historical data. So it's a very active area of science to really understand the exact shape of these curves using very complicated climate simulation models. And one example, or two examples of an earlier or more recent model are shown here, and the results haven't really changed much. So what's plotted here is the temperature response on planet Earth as a function of time following a sudden increase of the heating power on planet Earth. So we see that right after the start of heating at time 0, within about 10 years, 50% of the roughly final heating would have been attained. But it's not all, because the system would continue to heat at a slower rate. So essentially, what we have experienced so far as a result of a more or less sudden emission of greenhouse gases from a geological time scale is that we have realized more or less half of the heating that's already locked in. But if we were somehow holding greenhouse gas levels constant, the Earth will continue to heat, and the amount is roughly the same as what we have already experienced. All right, so so far we have had about 1.3 degrees Celsius of heating, and many people might welcome that as a beneficial change, especially for some people maybe living in very cold regions. But from an ecosystem perspective, that might not be such a very good news. So one example being the change in the population of bumblebees over comparing the start of the 20th century versus the start of the 21st century. So we have seen a decrease by up to 35% of bumblebee abundance in many parts of Europe and also North America. And if we compare the trend with the temperature trend, there seems to be a rather remarkable correlation. The authors of this paper examined these data sets and also other type of data sets, including land use, and concluded that these effects are independent of changing land use, which is often linked to the use of pesticides and also destruction of native ecosystems. But in this particular case, it seems that somehow the thermal perturbation could be a primary driving mechanism. And I like to point out that in locations where there have been some local cooling over the same time period, there seems to be an increase in the abundance of bumblebees. So such a trend would be counterintuitive if land use and pesticide use were of major concern for this particular type of organism. So, of course, insect biomass decay has been more generally observed in other studies, and an exponential description of the data suggests that they have decay constant half-life of only 12 years, more or less, and that's quite an alarming trend for a whole class of animals that's been successful for millions to billions of years to suddenly decay, like a fleeting radioisotope. So what could be behind thermally driven degradation of ecosystems and the fitness of species? It turns out that most life forms on Earth display what's called a thermal performance curve, denoted by this overall green curve that's bell-shaped. And it has a certain maximum at certain temperature that's can be denoted as the optimal temperature. And at above the optimal temperature, the performance of the species will decay. Today we'll not go into mechanistic details of why that's the case, but the same trend has been observed for animals, plants, and even bacteria and viruses. And essentially, if we go into extreme heat regime or have recurrent heat waves, the prediction based on these trends or individual thermal performance curves is that the fitness of different organisms would be greatly reduced, sometimes even driven to very acute local extinction for populations and individuals. One example is this controlled experiment where the experimenters installed these radiators in the field. And they gently heated these radiators, causing an average temperature rise in these regions of about 2 to 3 degrees Celsius. And over the course of a couple of decades of experiment, they observed that the fertility of this particular plant really plummeted to basically 0. And that the longevity of individual species that did succeed in germinating and going to develop to next life stages also decayed by a factor of 2 roughly. So combining reduced longevity of individuals and their infertility as a result of very gentle average temperature change, this plant in the experimental locations essentially went to local extinction or extirpation. So the sensitivity of plants to these very minor average temperature changes has also been observed in our crops. So a researcher at Cornell analyzed the productivity of our agricultural system and tried to explain an observed decrease in total factor productivity by multiple mechanisms. And he concluded that climate change is a major driver for this particular decay. And in fact, as we already pointed out, at about 30 degrees Celsius, photosynthesis efficiency start to decay, and also water stress really gets amplified. And that's the reason that explains a significant fraction of the decaying or decreasing productivity that we're observing. So here are probability density plots of the average land temperature comparing different periods, the recent past in color and roughly the 1950s. And we see a very remarkable shift of both the mean and also a spreading or widening of the variance or standard deviation. And what's really the most remarkable change is the probability for extreme weather events, usually denoted by things that happen at above 2 or 3 standard deviations away from the mean. So if we compare the area that's initially, say, here above 2 standard deviations in the original curve compared to what it has become in the new shifted probability density, we see that the increase is certainly more than linear and much more pronounced than the slow change in the mean. So summarizing like hundreds to thousands of studies, we were able to construct a diagram of habitability for current residents of Earth that include animals and plants. And we can superimpose on that habitability diagram the current trajectory of the Earth system and where we are taking it because of our energy structure. And we have already crossed certain thresholds that's becoming dangerous for ecosystems and species. And we're pretty much on track to surpassing 2 degrees Celsius in the next decade or 2. And this near-term trajectory turns out to be more or less independent of what we do in terms of the energy consumption and energy structure for the next decades. And we'll discuss a little bit of that in a later part of this presentation. The important thing to point out on this diagram is that there are certain regions along the CO2 axis that are also detrimental to ecosystems. On the lower end, we would be starving the plants because they need CO2 to photosynthesize. But on the higher end, would also be damaging marine and terrestrial ecosystems because CO2 becomes toxic and corrosive to their life processes due to the acidity of the compound when it's dissolved or combining with water or dissolved into aqueous environments. Put another way, the current trajectory is bringing the Earth system to a collision course with a thermal boundary long before the intrinsic problem of CO2 becomes apparent. And in fact, we do not have enough fossil fuel to induce a general toxicity from CO2 and acidification. So the most imminent problem we need to address is this thermal boundary. And this very simple analysis is confirmed by a more recent study looking at the onset of large-scale ecosystem impacts in different parts of the world. And we are here 2020, 2030, and there's already regions that are starting to undergo a large-scale ecosystem collapse. And this analysis doesn't even include the impact of extreme weather, as we have witnessed this year in Western Canada and the United States. So there are these very high-frequency extreme weather events that are generally not captured by analysis of this type, the climate analysis, which take multi-year and decadal averaging and making and smoothing out these excursion extreme events that can, in fact, have equal, if not more, damaging impact than what's shown here. So essentially, somehow we need to move the Earth system in the opposite direction, and especially in a direction that has a strong component pointing downwards along the temperature axis. But it doesn't really matter which way you go from ecosystem perspective. As long as we can go down, I think the ecosystem would be happy. To second order, if we want to really make a choice between going left or going right, ecosystem would vote going right for reasons we'll discuss at other occasions in this talk. And in fact, we can, allow for much higher atmospheric CO2 concentrations and still bring about a very rapid recovery of ecosystems as long as we can somehow cool down the whole planet. Now we know where to go, where we have to take planet Earth. Now let's examine whether solutions that are being proposed can actually deliver the impact that's necessary from ecosystem perspective. Now let's return to this diagram and notice that there are a few rate constants, the source rate and sink rate for either greenhouse gases or the heat. So we have already made it clear that the node that's important is this heat node. Therefore, the direct knobs are the rate that directly control how much heat is trapped in the atmosphere. So the other two rates that regulate how much greenhouse gas are in the atmosphere, those are indirect because they only impact what's really important through complicated mechanisms of coupling between the gases and heat. So examples of indirect methods include renewable energy, carbon capture sequestration, and all the CO2 capture proposals, either by nature or by using totally artificial factories. Geoengineering, particularly traditional corporate geoengineering, only focus on turning down the heat. And MEER reflection, we take an approach that make use of all different knobs that we have. But we're also very conscious of the engineering and the material limitations and time limits that humans have. Therefore, we use a triage process and the focus on what's most effective. And we will discuss why focusing on RS for heat is most effective. But we must also simultaneously and synergistically address the other knobs if we were to eventually return Earth to its initial state, or a state which allows it to eventually evolve toward a stability and a sustainability. So from the point of view of engineer, what makes a solution possible? The criteria are very stringent. We basically have to have yes to all of these questions. It has to work in principle on small scale. Not only that, we need to be able to implement at a full scale for the intended purpose and not be limited by how much raw material we have on Earth and how much energy we have as a civilization. On top of that, we have to be doing it fast enough. And the time scale is dictated by the dynamics of the Earth system and the response of ecosystems, which we have already viewed in previous slides. And that corresponds to single-digit decades. Maybe 3 if we're really lucky, but unlikely. So what's the scale of the problem we're up against? Again, we can take both the material perspective and the energy perspective. So in terms of mass, there is about 3 teraton of CO2 equivalent of greenhouse gases that we have dumped into the environment. That's roughly 10,000 times human biomass. And the energy problem, it's characterized by a power, basically the energy imbalance that's driving the problem. And the power is essentially the source rate of heat minus the sink rate, basically the net power that's being dumped onto the biosphere. And that power is known pretty precisely, and it's at the 430 terawatts. The reason why I give this range is because that 430 terawatt does not include a hidden amount of heating due to the fact that we're burning fossil fuels. And fossil fuel is causing these aerosols, which is reflecting the 570 roughly terawatts. So in comparison to this number, we have only 18 terawatts to work with. So that's how much heat we can produce right now as we're burning fossil fuels at the current rate. So essentially, the problem out there in the atmosphere is 50 times larger than what we have in terms of brute force fossil fuel power. And that's a very unfavorable ratio. And I want everybody to take a moment to think about that. I think it's also instructive to look at the problem visually. So imagine that's the amount of carbon in your body. This gigantic square is the amount of carbon in CO2 attributed to each one of you if we want to return Earth to a livable state. And you may say, it's doable. If I did one little block the same mass as myself a day, I might be able to somehow bury that away over some years. Yes, you can do that. It would take you 40 years and working full-time, 5 days a week, if you were to bury away your body mass of CO2 every day. That may be feasible, right? If it's already in a pile there as a coal that you can just bury away. The problem is that this CO2 exists as dilute gas that's well mixed into the environment. So I drew one pixel up here. I don't know if you can see. That little pixel is actually more concentrated than how much you can scrape up from an area or volume size of the slag. In fact, you have to imagine that this little tiny dot is uniformly distributed into a gazillion smaller dots in this area. And you, as a person, you have to go and sweep up those little bits from an area that's 1,000 times the size of this slide every day. So that's the challenge we're against if we are going to tackle this problem from just a material quantity point of view. And needless to say, that's a hopeless battle. So somehow we have to be augmented by our technology and our access to fossil fuel power. But from that perspective, the fossil fuel power you have is represented by this medium square, the other one being a higher quality electrical power, but so that's what you can get from burning coal and gasoline and natural gas. But the power of the climate monster is much larger. So some form of leverage must be designed into any solution that significantly amplifies the raw fossil fuel power each of us have access to. So having appreciated the size of the challenge, let's examine reforestation and afforestation from, first of all, a scalability point of view, the material scalability point of view. So this box represents how much we need to capture to stay safe. So unfortunately, the total capacity for trees, either by growing back, farmlands that we made use of by cutting down pristine forests, or by imposing forests onto locations or biomes that previously didn't even have trees. So these are the maximum amount of carbon we could capture on available locations on Earth. What's more, to fill those sinks, it takes on the order of 100 to 200 years. So essentially, if somehow we were blessed with alien technology and the alien extra power to perform the cleanup operation and not having, and also they would have to give us a food aid so to keep everybody alive. 100 years to 200 years later, we would have reduced the current problem by a small fraction. But does that really make a difference from a climate point of view? Let's examine that question. So these are plots of the albedo, or the reflectivity of a piece of land, as a function of the age of forest. We see that as forests grow and carbon gets captured, they become darker and they absorb more heat. So in fact, forests are not innocent from a climate impact perspective. And each meter squared of forest actually is capturing on the order of 10 to say 20 watt per meter squared of heat. So now let's examine the climate impact of this interconversion of two forms of carbon, either as atmospheric carbon or as forest carbon, and the impact of this interconversion on what really matters, the node, the heat node. So I'm using this expression, but don't be frightened. It's basically saying, okay, so the rate, the source rate of heat depends on the area of forests on Earth. As we just mentioned, the larger the forest area, the more heat is captured. So this expression essentially means that the rate at which heat is absorbed is proportional to the area of forests. So what happens is that, let's say in one hypothetical world, forests start to burn up, as is actually currently the case. So as the area decreases, the amount of heat that's coming in also decreases. And if somehow we increased forest coverage, then the expectation would be that the rate at which heat gets converted also increases. On the other side, the sink rate of heat is inversely proportional to the amount of CO2 in the atmosphere. So if part of the forest got converted into CO2, as we have recently observed, in the burning of Western forests, we would have an increase in atmospheric CO2 concentration, but also at the same time, a decrease in the rate at which heat or infrared radiation can escape into space. In another hypothetical world, where we were able to significantly decrease atmospheric CO2 concentration by putting them into forests, we would have cleared up the sky and increased the heat at which the rate at which heat can escape. But in the end, the size of this node would not have really changed from the original state, because let's say, as an example, let's say consider this as your bank. Now you're making say 500 a week, but you're spending 500 a week, and you have, say, like $50 in your bank, as an example. If you somehow only earned 10, but you only spent 10, then after a certain amount of weeks, the amount in your bank wouldn't have changed. Same thing goes for if you earned 10,000 a week, but then you squander that on some fancy sports car. In the end, your bank balance would have stayed the same. So all that is to say that the interconversion of different forms of carbon, either in CO2 in the atmosphere or as biomass stored in the forest, has overall a very negligible impact on the climate, as far as the amount of heat in the end that's trapped in the biosphere is concerned. So this slide is purely for illustration purposes, and it's not quantitatively accurate. So let's be a bit more quantitatively accurate. So for forests in Asia, the difference between the net difference, the climate impact for the two forms of carbon is very negligible, on the order of a few watt per meter squared for the same amount of CO2. In the US, it's slightly better. And what really makes a difference if somehow we can really have a really lush Amazonian forest in that case, because the aerial density of carbon gets so much larger in those lush forests, we can actually achieve a net cooling benefit. But unfortunately, as you have probably heard, Amazon has become a net source of carbon, which basically means right now, the natural process is for the conversion of forest biomass into atmospheric CO2. And the reverse process now is very difficult to maintain and foster under current climatic trends. So in summary, for mitigation using trees, the idea is to move some of this excess carbon into this additional sink. But as we have reviewed, there is actually a coupling between tree and also the climate, with the net impact being that it doesn't really matter if you move your debt from one bank to another. In the end, we still end up with more or less the same climatic outcome. Next, let's consider artificial means for reversing the process of CO2 emissions. So the problem here is that we have allowed a significant amount of energy to be wasted in letting more or less pure CO2 outgas into the atmosphere. To reverse the dilution process, basically to concentrate and to distill out the dilute CO2 back into a bottle of pure compound, is a very energy intensive process. And we're looking at roughly 6,000 exajoule of energy input if we wanted to return atmospheric CO2 concentration back to, say, 350 ppm. So the difficulty with that can be appreciated by considering separating out mixed salt and pepper. In comparison, US military uses only 1 exajoule per year. Therefore, from a simple energy perspective, we're looking at an operation which is, we need to be, a global task force that's maybe at least 100 times the size of US military to have a measurable impact on relevant timescale of decades to a century. But energy isn't everything in this industrial process. We also need to synthesize the chemicals and build the infrastructure. And the key chemicals are bases that have affinity for the dilute CO2 in the air, either sodium hydroxide or ammonia. To make those bases at relevant scales, we need to ramp up production by like 2 orders of magnitude. And in that process, we would need an amount of power which is comparable to the total power that we have available. In fact, if we want to simply undo 1 year of emissions captured back from the atmosphere, we need to invest 13 years of global energy production to undo 1 year of damage. And different forms of energy, like renewables or more efficient heat pumps, doesn't really help much. So here is, if you want to break even, we have to be more or less in the orange part, and we see that the US barely breaks even if we were to power this process using heat pumps. And there's also additional energy, material consumption production needed to support such an infrastructure. If our target is to capture 1% of current emissions, we need to increase concrete production by 5%. Essentially, if we were to double our global concrete production in order to do direct air capture, we would have only managed to capture 20% of our emissions. And the environmental impact, including toxicity to humans and also water usage, are also increased proportionally to how much we want to to capture back. So let's put everything together in some hopefully easier to understand diagrams. So the proposal for direct air capture amounts to moving the greenhouse gases into rocks, bury them into deep geological locations that's mechanistically decoupled from this heat. So that's the proposal. And let's use some, choose a number that's somewhat reasonable to do this assessment. We are currently outputting roughly 10 gigaton of carbon per year. So that's our industrial output. So let's just say we want to clean up at a rate which is comparable to our current emissions, or simply put, just to balance out, undo the current damage. Then we need to, foster a flux which is comparable to this 10 gigaton carbon per year. It's slightly more because, for example, as we saw on the previous slide, we have to build more infrastructure and increase concrete production. So the concrete needed to do this 10 gigaton carbon is roughly 3 gigatons. So in total, we need to do roughly more than 10 gigaton of carbon per year in order to balance out. Now, where would this energy come from? Of course, well, certainly have to come from the burning of fossil fuels in its various forms, either natural gas, petroleum, or coal. And I want to draw your attention to this number, roughly 1,400 gigaton carbon. That's how much fossil fuel reserve we have in the world. And that's not so much larger than the numbers we're talking about. Now, there's another thing we have to draw out, which is a arrow in the back, which basically denotes the CO2 we would have produced in running this air capture process from the air. And that gigantic flux of CO2 production, of course, somehow we have to also bury it into rocks, because otherwise we would be doing more damage to the atmosphere than we are cleaning up. So, and that flux is actually significantly higher than the cleaning flux, air cleaning flux. And that flux would be on the order of 100 gigaton carbon per year, which basically means we can only run such a crazy scheme for on the order of 10 to 20 years at max. And the process amounts to a transfer of all global fossil fuel reserve into rocks as CO2. In the process, producing a lot more industrial waste, including plastics and chemical, 9 times the current rate as far as thermal elastic plastics are concerned. And also in the same time, we would be actually dissipating a significant amount of heat just from the burning, because most of that process, is 95% of it is not doing useful work of capturing carbon. And that 95% is totally dissipated into heat. And I have, in this case, drawn the arrows to scale. So the width actually denotes how much excess heat will be dumping into the Earth biosphere. So this source of heat is actually from just burning a fossil fuel on the ground. And of course, we know from our model that if we increase the energy imbalance, the result is a further increase of the steady state. Well, actually, in this case, it's not steady state of the rate at which heat will continue to accumulate. So why does such a crazy process get funding? It's a very interesting question. I think, personally, I think it's big. It's essentially because, it's a process that accelerates consumption. It accelerates the extraction of resources, and it also provides profit in the short term. And that's the bottom line of our economy. So as crazy as this might look, it's the dominant solution that's presented to policymakers everywhere in the world. And the less crazy proposal for green renewable energies comes with a catch. So there's accumulating greenhouse gas in the environment as a result of using fossil fuel, but also there's a steady state of cooling particles as a result of burning. Renewable energy is important because it would allow us to more or less stabilize the level of greenhouse gases. And that's a first step to tackling the climate process. But the slight downside to that is, as soon as we are able to stabilize that by stopping to burn them, this component, the anthropogenic aerosols, would very quickly dissipate. And right now they have a negative radiative forcing impact. Basically, they're cooling the planet. So we would be left with a slightly higher energy imbalance and a faster rate of warming on the planet. And so that essentially means that renewable energy, while being a necessary ingredient to the long road to sustainability, cannot be relied on as a solution to the climate crisis as far as ecosystem response is concerned. And we have seen this slide. So losing the aerosol amounts to inducing a step change on the order of 1 watt per meter squared. And that would in turn leads to a very rapid rise in temperature of roughly 0.5 to 1 degree Celsius in the short term, and more, roughly double that in the longer term. So a summary of the assessment is quite clear. Renewable energies do not in principle help us to solve the climate crisis, and natural and technical ways to draw down are not feasible. And in fact, there's no proposal in the mainstream that could even in principle be beneficial to addressing the climate catastrophe. So now let's move on to MEER reflection framework. So at MEER reflection, we refuse to take anything for granted. And we always want to examine things from multiple perspectives and from different angles. And one example being the impact of CO2 on different physical parameters in the environment. One particular impact of CO2 that's not really talked about is its ability to provide water-saving properties to plants, and its impact on fertilizing plant growth. So we all know that plants take CO2 through their leaves, specifically pores or holes on their leaf called stomata, and then they use sunlight and this carbon source to make complex sugars. So the first step is the diffusion of the primary material, CO2, into the leaves. When you have a higher concentration of CO2 in the air, the carbon diffuses into the leaves faster and more efficiently. So that's why plant can grow faster with a higher external CO2 concentration. And also the stomata through which the CO2 enters the leaves can be closed and be smaller while still maintaining the same inward flux of CO2. A smaller opening on the leaves is sort of like a smaller damage holes on the leaf, which would enable water to be lost at a slower rate. And that's why when you have a higher concentration of CO2 on the outside, plants use water more efficiently. And that makes them more drought resistant. So that benefit is very well established in the plant physiology and agricultural field, but it's not really examined in the context of climate change mitigation and adaptation. And that's one angle we need to be aware of. So given the multi-dimensional impact of CO2 and their various manifestations on different timescales, if we could somehow, in the short term, just with laser sharp focus, take out the heating impact while preserving the fertilization potential and water saving potential, then we would have converted a former enemy into an ally in this transition toward sustainability. So how do we do that? You're here because you have already followed our project for a while, and we plan to use glass mirrors to undo the warming effect of CO2 by providing a proportional cooling radiative forcing. And I won't go through the calculations, but suffice it to say that after much assessment, we have come to the conclusion that roughly 10 meters squared of MEER installed on many parts of the world's land surface is sufficient to cancel out the heating effect of 1 ton of CO2. And the price for making the required device ranges somewhere between $1 and $10. On the lower end, it's the energy for the fossil fuel used to melt the glass. On the higher end, it's what you can buy currently in bulk quantities. So if the process were to be done in a coordinated fashion, the production cost should situate somewhere in between $1 and $10. It's quite important actually to consider the material specifics. The reason being that while you can make reflective things from different types of materials, including organic films and also metals, it's not suitable if we're going to scale this process because of the gigantic surface area that needs to be covered. And the only process or only material that's compatible with this engineering task is soda-lime glass. The reason being that it's composed of the most abundant elements in the Earth crust. These are so abundant that in fact we already have a proven reserve in soda-lime glass that can enable making enough mirrors to cancel the heating of 1,100 ppm CO2 equivalent, which is way beyond what we can humanly achieve by burning all the fossil fuel reserve on planet Earth. So at least it's feasible and scalable. But of course, that's not in state of the planet we want to go. We want to halt progress towards such foreign environments as soon as possible by leveraging the other capabilities of glass and glass mirrors. How do we do that? We now appreciate why it's important to have cooling mirrors outside before engaging in ramping down on fossil fuels because of the heating that comes with decarbonizing. And the impact of reducing, say, flight at the beginning of COVID is quite clear. When the flight numbers decrease, the amount of sunlight reaching Earth drastically increase. Specifically, the component, which is what we call direct irradiance, basically light that comes in without having been scattered by aerosols or cloud. But overall, the power arriving on Earth also is significantly increased compared to previous years. So we know that the effect of cooling is real and needs to be taken into account in engineering the trajectory. So as we slowly ramp down fossil fuels, the sky becomes clear, as we just saw, and that enables a range of concentrating solar technologies to perform better. And higher efficiency from renewables would then in turn catalyze a faster waning of our dependence on fossil fuels. So it's a exactly positive feedback that we desperately need because of the multiple feedback that are negative in the climate system. And we'll discuss how MEERs can provide a very strong local cooling, and that would safeguard agriculture and enable the recovery of ecosystems, because trees are also plants, and they also need, protection from droughts and extreme thermal events. So in a sense, MEERs and natural solutions should work synergistically in their common quest to ramping down fossil fuel dependence and also cleaning up the planet's atmosphere. I'd like to present some initial data conducted and from experiments that people on our team have conducted. So here we have an image of two test MEERs. We see that what you see on the MEERs are very different. Why is that? It basically reflects the fact that photons, hitting the ground at the bottom of the atmosphere come from a variety of different directions, and the intensity of photons from different directions are different from the different scattering processes in the atmosphere. For example, scattering from clouds. So on a typical day, a clear sky day, I think Jagger found that up to 1,000 watt per meter squared of initial solar irradiance can reach ground without being scattered. And there's some scattering, but most of it, a large proportion, can arrive at ground. And after interacting with the MEER in specular reflection and going out of the atmosphere, we have from 70 to 80% going out directly. So that basically shows that installing MEERs at the bottom of the atmosphere is efficient for rejecting out shortwave radiation. And the efficiency of that can be up to 70 to 80%. One can also perform a more top-down analysis, looking at the efficiency as a function of the location, and averaged over the year, and also different locations. On average, we can expect roughly 100 watt per meter squared of cooling. So in the next slides, we will examine the initial puzzle of how it's possible to use a small amount of power to overcome a power which is much larger. So let's assume that you as an individual use all the energy you have for the next year to make MEERs. Let's say everybody decided to just take 1 year to donate their energy to that process. And let's say that's how much you have made at the end of 1 year. And you put this MEER out at the angle that best matches your surroundings. After 1 month of deployment in your neighborhood, you would have a rejected amount of energy, which when normalized to the 1 year time corresponds to this amount of cooling power. So that's the impact of the MEER after 1 month. If you let it sit outside for a year, the amount of cooling power effectively would have increased, because once the MEER is installed, it's passively working as long as you don't break it, and it will just be giving you benefit over time, and you reap the profit, and that's how much you gain is a function of time that you let it sit out there. So that's the fundamental mechanism by which we can use the longevity and stability of a passive device to gain an upper hand on the thermal power that we're fighting against. So an analogy that we usually make is a difference between an active cooling device, such as an air conditioner, with a passive cooling device. In the active cooling device, one has to continuously supply electricity. And for every joule of electricity, you get 3 joules of heat outside of your house. So the ratio defined by the powers is roughly 3, coefficient of performance. In the case of MEER, the energy input is just a one-time input, represented by the heat used to melt and coat the glass, and let's call it Q prime. But after a year, the amount of heat that this device would have ejected from Earth is actually 100 times the amount of heat used in its manufacturing. That was a quite surprising number when we first did calculation, but it's actually verified number. So in a sense, if say over 30 years, which is a very easily achievable lifetime for such a device, you would have amplified your initial power by a factor of 3,000. And this amplification, due to quality and longevity of the device, is the fundamental reason why we can achieve the seemingly impossible task of overpowering a warping power that's significantly larger than what we have in terms of fossil fuel power. Not to mention that, of course, you're running your AC, you're adding heat to the planet indirectly through the CO2 pollution. So we have so far taken the perspective of global mitigation potential. Let's look at some local impacts, which we think are some distinguishing features of MEER reflection framework, which brings immediate local benefits. So our theoretical team and experimental team have together collected data and made simulation of the cooling area, cooling power density in the month of July, this past July, using actually measured solar irradiance data in Plymouth, New Hampshire. So what we're looking at is a top-down view of a piece of land. The x-axis denotes east-west axis, and the north-south axis denotes basically, so it's drawn to scale. So I think we made a 1-to-1. So it's actually very much drawn to scale, and the white rectangle is represent the edges of the MEER. And the white dot is a sensor that we used to measure the temperature of the soil. One can also assess the cooling pattern for a MEER which is slightly higher from the ground at 1 meter, and compared to a lower height MEER, the impact is as a smearing out and averaging of the cooling power over a larger area. So there is a tunability of the degree of impact you want to achieve by just playing around with the geometry of the installation. And here are cross-sectional profiles of cooling impact as a function of 3 different heights. And we see that if the goal is to have uniform cooling, the trick is to make them higher up, lifting from the ground. And in fact, I think this trend can be extrapolated to the case of, say, space MEERs or stratospheric aerosol injection, which are high altitude perturbations. And in those cases, it's very difficult, basically impossible, to have spatial control or spatial specificity because the impact happens so far. So we would have a uniform decrease, which is a very limiting aspect of those approaches. So here are the sensor readouts comparing a sensor underneath a MEER versus a sensor in a neighboring location that's not directly shaded, but still experience some of the cooling, we think. And here are the difference, which really highlights that it's possible to cool the soil at 10 centimeter depth up to 5 degrees Celsius on very sunny days. Here are what's called a power spectral density of the different data sets. The orange one being the power of the sun, which is driving the whole process. And the temperature anomaly are essentially responses of the soil to this solar drive. And we see a very strong peak at a frequency of 1 day inverse, basically representing the diurnal cycles. We can really focus attention on this diurnal cycle to extract out some very simple relationship between solar power and the cooling impact. We won't go into details of how that's done, but suffice it to say, we can reduce a rather complex set of time series into a bunch of just proportional lines. And we can expect up to 4 degrees Celsius of cooling for in locations where you have a very clear sky, giving you 1 sun of the solar irradiance. There's also a correlation between the diurnal temperature variation and the amount of cooling in the soil. The particular experiment was conducted in New Hampshire, where diurnal temperature swing was around 10 Celsius or roughly 20 degrees Fahrenheit. So if this relationship held in other locations, we can expect much more dramatic cooling effects, especially in regions that are especially hard hit by climate change and extreme weather. So to conclude, I'd like to recapitulate some of the findings we have found in some simple to remember numbers. One is that if we're concerned about sequestering carbon, the effective virtual sequestration potential of the capacity of the MEER is roughly 3 times that of Amazonian forest, 6 times that of boreal forest, and more than 10 times that of monocultures. From a climate perspective, the MEERs are roughly an order of magnitude more efficient on a per area basis. So it's obvious that planting a MEER has a much higher climate benefits, from a return to cost ratio consideration compared to planting trees, which these days have a really hard time surviving. Pretty much comparable ratios for the Arctic ice, because MEERs, when they're installed in sunny areas, they can work over a larger fraction of the year compared to the poles, which are not lit over a significant fraction of the year. And people on our team, including Jonathan, are working on inspiring the youth and also bringing this idea to the youth in the hope that they would both learn the science and also spread the message more widely. And in fact, if somehow we could plant the seed of the idea into student leaders' mind and then mobilize the 14 million strong army of kids to carry these science, they can together completely dwarf the capacity of industrial direct air capture almost essentially over a week. They can achieve that if each of them just followed a simple recipe that we will hopefully be able to provide very soon. And I was giving talk to a bunch of privileged kids at Westminster School a while back, and their school could have a comparable climate impact compared to this much more expensive dedicated power capture plant in Switzerland by devoting what would amount to chump change for parents of these privileged individuals. So in closing, I'd like to thank Dr. Edwin Lind for his vision, for enabling this sort of investigation that's outside of the box, unfettered by dictates of the necessity to pay rent for at least a couple of years. And I'd like to thank all members of MEER ReflEction, all the students, volunteers, and donors. You are numerous and you're among the audience, and thank you. And also collaborators, list for whom is growing constantly. And also thank you for joining us and for bearing with me over this past hour of what must have been a very technical presentation, and hope you were able to learn something new, and also we look forward to your feedback.